Okay, let's just jump right in. If you are responsible for securing infrastructure in, a dynamic multi-cloud environment, we're talking Azure, AWS, everything in between, the sheer amount of stuff you need to know can feel like drinking from a fire hose.
Oh, it absolutely is.
It's overwhelming, especially when the goalposts are always moving with auto-scaling and continuous deployments.
Right, because you're not just dealing with perimeter defenses anymore. You're dealing with identity as the new perimeter.
Yeah.
Infrastructure is defined as code. Network routing shifts constantly. You have to secure the architecture from like the very first line of code.
Exactly.
Yeah.
So for this deep dive, we're really trying to cut through all that noise. We're taking the core framework of what defines a robust, high-level cloud security architecture.
And we're boiling it down.
We're boiling it down to the 10 most practical, high-leverage knowledge nuggets that you really need to know today.
And we've organized this into 4 key themes. First, how we build and secure the foundation. Then, how we control traffic flow across the network dynamically. Third, how we get that deep visibility we need. And finally, how we bake security into the application development process itself. So let's start with the foundation, automation and identity.
When we talk about cloud security, we have to start with automation. That's where efficiency meets scale and security.
Right.
So if you're deploying multiple security appliances, say a dozen FortiGate instances across a few regions, a tool like Ansible is it's foundational.
Mm-hmm.
To make that work efficiently, where does the administrator have to define which remote devices to target and, how to connect to them?
Well, that definition has to live in a centralized inventory file. This is, that separation of concerns that really defines good infrastructure as code architecture.
Okay, so why is that separation so critical? I mean, couldn't an engineer just hard code the device specifics into a template or the playbook itself?
They could, but that defeats the entire point of automation at scale. If you centralize all that device info in the inventory file, you can then reuse your playbooks and your roles pretty much universally.
No.
The playbook handles the what like installing a policy, and the inventory handles the where. You're not embedding device-specific info into every single task.
Which means any update, say a credential or an IK address, is made in one place.
Exactly. It reduces configuration drift and, honestly, just human error.
That abstraction is so powerful. And speaking of abstraction with infrastructure as code, let's switch over to Azure. A lot of organizations, they started out using those standard JSON-based ARM templates.
Oh, yeah, the walls of text.
Walls of text, but now there's this huge push towards Azure Bicep. What is the most compelling advantage of shifting to Bicep for these big, complex deployments?
The key advantage is just simplicity. Readability and structure. Bicep offers a simpler syntax and better modularity for managing complex resources. It's so much cleaner than those incredibly verbose JSON templates.
Anyone who has tried to debug a 500-line JSON ARM template knows that pain. So that abstraction Bicep offers, it means you can define resources in logical groups, making these huge deployments easier to read, easier to maintain, and crucially, faster to troubleshoot.
And that leads directly into security. Because when you deploy these automated resources, the security appliance, that FortiGate for instance, it needs a secure identity to talk to the cloud platform.
Right.
So if an admin is setting up a FortiGate SDN connector for Azure, and their goal is to completely avoid the massive security risk of managing manual credentials, what secure method should they be using on the Azure side?
So they need a way to communicate securely without storing any static secrets. What's the solution?
The secure authentication method they need to enable is system-assigned managed identity.
And this is where that identity as the perimeter ID really comes into focus, isn't it?
It is.
Why is a system-assigned identity so much better than, say, using a key vault to store a secret?
Because Azure automatically manages the entire identity lifecycle for you. You are completely eliminating the risk that comes with manually creating, rotating, storing, and retrieving static passwords or keys.
So the cloud platform is just handling all the credential rotation behind the scenes.
It is. It's an identity that the system manages for the system. It closes off a huge attack vector that, traditional security models basically created. You automate the identity, you eliminate human error.
Okay, so we've automated the build, we secured the identity. Now we need the network itself to handle traffic dynamically. Let's look at a critical scaling scenario in Azure.
Okay.
Imagine a company prepping for peak web traffic, maybe a big product launch or Black Friday. They need their firewall cluster to automatically expand or contract based on the volume of traffic coming in. What essential Azure feature makes that possible?
That capability for elastic security capacity is achieved through virtual machine scale sets.
So what's the architectural implication there? Why is that such a game changer compared to just, over-provisioning hardware?
It's the dynamic adjustment. You're ensuring both resilience and cost efficiency. Your firewall cluster can scale out instantly to handle a huge DDoS attempt or a traffic surge, which guarantees high availability.
And then when traffic dies down, it scales back in.
It scales back in, reducing your compute costs. It moves security from a static, worst-case scenario calculation to a pay-as-you-go responsive model.
This level of dynamism really ties into the next big challenge: centralized routing, especially in complex multi-VPC architectures in AWS. And this is where it gets really interesting, because the routing needs to be forced through a central security VPC using something like a Transit Gateway Connect architecture.
Yep.
Needs symmetric controlled traffic flow.
Right, and that requires 3 very distinct non-negotiable routing steps.
And it's a classic inspection architecture, right? If you miss one step, traffic either breaks or it just bypasses security completely.
Exactly. So the first step is about getting the traffic to the hub. You have to point the default route in the spoke VPC to the transit gateway. That tells the satellite networks where to send their unknown traffic.
Okay, so the spoke VPC knows to go to the TGW. What's step 2? The handoff to the security appliance itself.
The second step is inside the transit gateway's own routing table. You have to direct traffic from the transit gateway subnet to the FortiGate internal interface. This makes sure the traffic actually hits the firewall for inspection,
instead of just going straight to its destination. And what's the final step, the one that people often forget that guarantees the conversation is symmetric?
Finally, you have to configure the FortiGate's internal routing table to send traffic back to the transit gateway. This ensures the path is clean, it's symmetric. A really common failure we see is when administrators miss that internal firewall route.
So the traffic gets to the firewall.
Right, it gets there. But then the firewall has no idea where to send it next, so the sessions just stall and the connection fails. Those 3 steps are absolutely essential.
That level of detail is critical. Now, let's pivot back to just fundamental filtering. Let's look at AWS Network Access Control Lists, or NACLs.
Ah, yes.
This is a common trip-up point because of how the rules are evaluated. So, if an AWS admin is trying to block some malicious traffic at the subnet level, but they already have a broad rule at position 100 that allows all traffic, where does the new deny rule have to go to actually be effective?
It has to be placed at any position between 1 and 99.
So why does the number matter so much in NACLs? I mean, we're used to stateful firewalls where the most specific rule usually wins, regardless of the order.
That is the crucial difference. NACLs are stateless. They don't track connections, and they are evaluated sequentially from the lowest rule number to the highest.
So if Rule 100 says allow all, anything that hits it is just allowed, period.
Period. If you put your deny rule at 101, it will never even be reached. The block rule must be evaluated before that permissive rule.
Yeah.
That stateless nature makes understanding rule order just mandatory.
All right, let's move into visibility and modern application protection. Our infrastructure is deployed, it's running, it's routing traffic. Now we need to know where the actual risk is.
Right.
An admin using a cloud security posture management solution like FortiCNP is monitoring hundreds of resources. They can't chase every single alert. They have to prioritize. What feature lets them do that based on actual risk?
That feature is Resource Risk Insights.
And this is about moving beyond just raw vulnerability scoring, right? I mean, if something has a high CVSS score, but it's sitting on a private, unexposed network, its operational risk is way lower than a misconfiguration on an internet-facing endpoint.
Exactly. Resource Risk Insights doesn't just count vulnerabilities. It correlates security findings with contextual risk factors like exposure, compliance, identity access, the potential blast radius.
So it turns a technical finding into a business risk score.
It does, which lets you do risk-based remediation. You attack the highest risk items first. It's crucial for security team efficiency.
But to analyze that risk, you need raw data. If an admin needs to do a deep forensic analysis of specific network traffic patterns, for instance, going way beyond general metrics, what native cloud feature has to be enabled?
The answer there is flow logs at the network interface level.
And why the emphasis on interface level?
Because flow logs are the source of truth for all IP traffic activity. They capture detailed metadata about every single IP flow source, destination, protocol, ports, and the action, accept or reject for a specific network interface. This is the forensic gold standard.
Without that, you can't trace a specific connection attempt from a potential attacker.
You can't. Flow logs give you the granular data you need to trace patterns, investigate breaches, and confirm your filters are actually working.
Let's pivot to the modern challenge of containers and microservices. We're pretty good at protecting north-south traffic data coming in and out, but what about east-west traffic? That internal movement between microservices inside a cluster.
That's a tough one.
That internal movement needs protection. The source material highlights two distinct methods for securing it. What are they?
Yeah, this is complex because microservices are constantly spinning up and down. The first method is enforcing network control, implementing label-aware policies on a FortiGate next-generation firewall.
And the power of that is that the policy isn't tied to a static IP address, right?
Precisely. The security enforcement dynamically follows the Kubernetes labels no matter where the microservice spins up or what IP it gets. The security context moves with the workload.
Okay, so that's method one. What's the second?
The second method targets the application layer for that internal communication, deploying a FortiWeb ingress controller to inspect incoming application traffic.
So one handles network routing based on workload identity, and the other handles deep application layer protection for the components themselves. This complexity is why we now talk about DevSecOps, integrating security right into the pipeline before anything even hits production. So if we look at a solution like FortiDevSec for scanning container images, what two key security scanning capabilities does it provide?
It provides static application security testing, or SAST, and software composition analysis, SCA.
Explain the difference. Where does SAST look, and why is SCA so mandatory now?
So SAST finds vulnerabilities right in your own source code, things like coding flaws, potential injection points before the app is even compiled. SCA, on the other hand, is critical because modern apps rely so heavily on third-party libraries and open-source components. SCA identifies risks and known vulnerabilities in all those dependencies. You have to secure both your original code and all the code you import to get a complete picture of application risk.
The discussion today focused on infrastructure that can instantly scale up, provision identity automatically, and apply security rules dynamically based on labels. What fundamental assumptions about your current on-prem or traditional security architecture, like relying on fixed IP addresses or manual capacity planning, are rendered obsolete by the dynamic, identity-driven, and highly automated scaling capabilities of the cloud infrastructure we discussed today? Think about that next time you plan a deployment.